Hello and welcome to this Any Excuse for a Chemistry experiment from here, Munro Towers. What we're going to do is we're going to have a look at Year 9s today, and we're going to be following this revision guide. Hopefully you've got it. If you haven't got that revision guide, then choose one that you have. We're going to be looking at electrolysis. It's part of the chemical changes topic. Now, electrolysis is a separating method, but it's different from all of the other separating methods that we've ever seen before. This one is a separating method that separates ionic compounds, and we've got to do it in one of two ways. That ionic compound has to be either molten or it needs to be dissolved in another substance, usually water, but we are going to see an example of it when it's not water. Now we're going to need to know a couple of disciplines here. First one is the equipment that we need to use. We're going to start off with this piece of equipment. This is called the electrolysis cell, and it's the container where electrolysis is going to take place. We're also going to need two pieces of material that can conduct electricity. We're going to call these our electrodes. Our electrodes are going to be needing to be attached to a power supply for some electricity. And the last thing is our ionic compound that needs to be separated. This is going to be our electrolyte. Our first example of electrolysis is going to be a simple binary ionic compound. A binary compound. A binary compound only contains two things. We've got a lead ion, Pb2+, and a bromide ion, Br-. Now, because the lead has got a 2+ and the bromide has only got a 1-, we're going to need actually two bromide ions for every lead ion that we're doing. Now, lead bromide, because it is a binary compound that we're separating, is going to need to be molten. So we're going to need to heat this up. The reason that our electrolyte must be molten or dissolved in water is because we want the ions to be able to move or flow. So if I have my lead ion in there and my Br- ions there, then we're ready to go. We've heated them up, they're now molten, they're free to move. Now we're going to turn the electricity on our electrolysis cell. We're going to have a positive electrode and a negative electrode. Now what's going to happen is, as we turn the electricity on, the positive electrode is going to attract the negative ions. And the negative electrode is going to be attracting the positive ions. Let's have a look at the two equations that are going to be taking place. Our negative ions were attracted to the positive electrode, and when they get there, they want to turn from an ion into an element. You've got to remember, electrolysis is a separating method which separates ionic compounds into elements. So our element at the end of this must be bromine. So we've got two bromide ions. They're going to go to the electrode and they will turn into bromine gas. So they go to here and they deposit 1, 2 electrons and produce bromine. Now, we've got to take into account the electrons that are being transferred. So we're going to use the symbol an E- for our electrons. Because I've got two bromide ions in each, I've got 1. In total, I would deposit 2 electrons into my circuit. Let's have a look at what happens with the lead ion. The lead ion is attracted to the negative electrode. So we're going to start off with our lead ion. It's going to gain those 2 electrons to turn into our element lead. Now we're going to move on to our second example of electrolysis. This one is aluminium oxide. Now this one might appear to be a binary compound. However, what we're going to have to do is we're going to have to manipulate it in order to do our electrolysis. The melting point of aluminium oxide is about 2000 degrees Celsius. Just think about the amount of energy it's going to take to heat that up and then keep it at that temperature, and then the cost of all that electricity. So we're going to have to do something about that. What we do is we dissolve it into a very weak or very poor sample or source of aluminium oxide. This is called bauxite, B-A-U-X-I-T-E. Now bauxite has a much lower melting point. It's actually about 950 degrees Celsius. We need to remember both of those things. We need to remember that we use bauxite and that it has a significantly lower boiling point. So we can dissolve our aluminium oxide into our bauxite at a much lower temperature. So here we are. Here is our electrolyte, is our aluminium oxide. We have aluminium ions, and we have oxide ions as well. Oh, sorry. Now we're going to turn the electricity on, but if you've noticed, I've only got one lead coming into my circuit here. This is because our positive ion, our positive electrode is our electrode that dips into our electrolyte, but the container itself happens to be the negative electrode. And it makes sense really. I've got a nice container here. I'm going to be trying to extract the aluminium from aluminium oxide, and if I have my container as the negative electrode, the positive metal ions will be attracted to it, and I should end up with my aluminium at the bottom. Let's have a look and see what happens. We'll start off with aluminium. Our aluminium with a 3+ charge is going to have to gain 3 electrons to form aluminium. But if you can see, I've got 2 of those because my formula for aluminium oxide is Al2O3. So if I have 2 lots of those, I'm going to need to have 6 lots of those to make 2 lots of aluminium. Let's have a look what happens with our oxygen or our oxide ions. So we are going to start off with our oxide ions. And I've got 3 of them, 1, 2, 3. They're going to go to the electrode and they're going to turn into oxygen gas. Remember, electrolysis is a separating method that separates an ionic compound into elements. 3 lots of oxygen ions turn into 1.5 moles worth of oxygen, and then I would return 3 electrons. Sorry, each of those contains 2, so that's 6 electrons into the circuit. One other thing happens here. My electrode, my positive electrode, is actually made out of carbon, and the carbon reacts with the oxygen that is produced here to produce carbon dioxide. So actually what ends up happening is my electrode here wears away and I produce not oxygen gas here but carbon dioxide. So my carbon electrode wears away, the oxygen that would be produced reacts with the carbon to produce carbon dioxide. A 6-mark question might include a question about the environmental impacts of extracting aluminium from aluminium oxide. We've got to remember, we've got to heat it up to 950 degrees Celsius. We've got the electricity that is being generated from probably fossil fuel power stations, and we also have carbon dioxide being produced. So our last look at electrolysis is probably the most challenging one. It's also got lots of bits that we're going to need to remember off by heart. It is the electrolysis of aqueous solutions. Now, aqueous solutions means our ionic compound has been dissolved in water. This presents us with a new problem. Not only do we have the positive ion from our ionic compound and the negative ion from the ionic compound, but the water will also separate into two ions, a hydrogen ion, H+, and a hydroxide ion, an OH-. And we're going to have some rules to determine which of the two positive ions goes to the negative electrode and which of the negative ions goes to the positive electrode. Right then, we've got two rules that we need to remember when we're looking at the electrolysis of aqueous solutions. The first thing is we're going to look at is what happens at the negative electrode. Now, the negative electrode is going to attract the positive ion. Now, if you can remember, in our aqueous solutions, we've got the metal ion, which is positively charged. We've got the non-metal ion in our ionic compound, which is negatively charged. We've also got, from our water, a hydrogen ion and a hydroxide ion. OH-. There we go. So we have to decide, that looks like a D. We're going to have to decide which of these is going to be attracted. So, rule 1. At the negative electrode, it's going to attract either the metal ion or the hydrogen ion. So, if the metal is more reactive than hydrogen, hydrogen gas forms. Now, if you can remember from your reactivity series, hydrogen is right the way down the bottom, but there are some metals that are less reactive. So if the metal is less reactive than hydrogen, the metal forms. Usually, in our exam, the only metal that this will be is copper. So there's rule 1. If the metal is more reactive than hydrogen, hydrogen gas forms. If the metal is less reactive than hydrogen, the metal forms. So we've got our positive ions sorted. Rule 2. They're going to have our non-metal ion, or we're going to have a hydroxide ion. Now, this one's going to be fairly straightforward. If there is a halide, now a halide is going to be either a chloride ion or a bromide ion or an iodide ion. Their gas will form. So we should see Cl2, Br2 or I2. If no halide is present, oxygen gas forms. And we need to remember this equation because it involves splitting apart our hydroxide ion. Let's have a look at the half equations that show the movement of electrons as those ions turn into elements. Let's pick on our metal here. So if the metal is more reactive than hydrogen, then hydrogen gas will form. So our hydrogen gas is going to have to gain electrons to form hydrogen gas. Now the formula for hydrogen gas is H2. Put a little state symbol in there, which means I need to have 2 of these, and I'll end up with 2 electrons needing to be combined. However, if the metal is less reactive than hydrogen, the metal forms. So our example would be copper. Now copper is a 2+ charge. It's going to need to gain 2 electrons and it's going to form copper metal. Let's have a look at rule 2. If there is a halide present, chloride, bromide or iodide, their gas will form. So here we go. Our chloride ions are going to turn into chlorine gas. Now chlorine gas has got a formula of Cl2 and it's going to deposit those electrons into the circuit. I've got 2 chlorine atoms here bonded together, so I'm going to have 2 chloride ions to start with, and it's going to be 2 electrons. Now this is the more challenging one. If no halide is present, oxygen gas will form. So I know that I'm going to have oxygen gas. And I know that it's going to come from my hydroxide ion. I'm also going to produce water, and I'm going to lose those electrons into the circuit. Now our job is to balance it out. If I have a look over here, I've got 2 oxygens and 3 oxygens, but I've got an even number of hydrogens there. So I'm going to have an even number on this side. So I'm going to have 4 hydroxide ions. That gives me 4 oxygens, 2 here, and I can have 2 there. I've got 4 hydrogens, giving me 2 times 2, that's 4 hydrogens. So my atoms are now balanced. I can't forget those electrons. I've got 4 lots of electrons, so I'm going to have 4 electrons there. Now, if you're not strong with balancing your symbol equations like this, then you're going to have to remember this one off by heart. If no halide is present, oxygen gas will form. So 4 hydroxide ions break into oxygen, gas, and 2 water molecules and deposit 4 electrons. There we have it. All we need to know about the electrolysis of ionic compounds. Got to remember, it's a separating method, separating ionic compounds into elements. We have binary compounds which need to be heated up and molten, and the rest of them need to be dissolved. The example of extracting aluminium from aluminium oxide gets dissolved in bauxite, but we also need to know those 2 rules for the electrolysis of aqueous solutions. What you need to do now is you need to go and find some questions. Either look in your book there, look, we've got a whole row of questions there that we can use, or go onto the T drive and look at those tasks that have been set for you already. Next video we'll look at is acids and alkalis. Thank you and goodbye.